And thanks again, everyone, for being here. Yeah, I'm going to be talking with Evie today about BOWIE-ALIGN, which I'm sure many of you have heard of, many of you are part of the team. And essentially what we've been doing is comparing orbital alignments and atmospheric compositions to probe hot Jupiter origins. But BOWIE-ALIGN actually was born out of the first BOWIE meeting back in December of 2022. Um, and so I just want to say, and I'm sure Evie will echo this as well, it's been a real pleasure and a privilege to be part of this network. I've really enjoyed it these last few years, and I'm really excited to continue working with everyone in the future as well. But getting then down to BOWIE-ALIGN. So to motivate BOWIE-ALIGN, really I want to start with this slide here, which we are all very familiar with, I'm sure, the population of transiting exoplanets that are shown as these little red dots with their sizes on the y-axis against their orbital period on the x-axis. And clearly, these exoplanets occupy a very different part of this parameter space to the solar system's planets. And this has fundamentally challenged our understanding of how planets form and evolve. And there are lots of different questions around different subpopulations of this overall population. But for today, what we're going to be focusing on are the population of hot Jupiters up here, and specifically how and where these planets form. So moving on to the first part of this question, how do hot Jupiters form? And really, there are two main ways in which planets are thought to form, either via core accretion, which is shown in this top panel here, whereby the planet forms from the gradual accumulation of solid material until it reaches some critical mass, by when it will then undergo runaway gas accretion. Or the second scenario, which is shown in the lower panel here, occurs more like how stars form via gravitational or disk instability, where you have these overdense regions of the protoplanetary disk which collapse under their own gravity. And actually, there is a growing body of evidence that seems to suggest that hot Jupiters form via core accretion. And this is perhaps most famously known from this plot in a paper in 2005, which shows the occurrence rate of hot Jupiters around stars of different metallicity. And essentially, what these authors showed is that more metal-rich stars are more likely to host a hot Jupiter. And this has been taken as evidence for the core accretion scenario of formation, essentially because you have more metals in the disk and a larger solid surface density, meaning that there is more solid material available to assemble massive cores before the protoplanetary disk disperses. But we'd also like another method to distinguish between these two scenarios, and that could come via the measurement of a mass-metallicity relation. So this plot here on the right-hand side shows the metallicity of the solar system's giant planets against their masses on the x-axis, along with the hot Jupiter WASP-43b that was measured back in 2014 by Laura Kreidberg et al. Using the Hubble Space Telescope. Now you can clearly see that the less massive Uranus and Neptune have more metal-rich atmospheres than the more massive Saturn and Jupiter. And this again is taken as evidence for core accretion, essentially because these less massive hydrogen and helium envelopes are more readily polluted by infalling solid material. If the solar system planets instead form via gravitational instability, we may expect their atmospheres to be more solar-like in composition. So understanding whether or not hot Jupiters follow a mass-metallicity relation has been a long-standing goal of the field. And this here is a fairly recent compilation of hot Jupiters with measured near-infrared JWST spectra. And while the exact functional form of any mass-metallicity relation remains uncertain, there does at least appear to be a dependence of a hot Jupiter's metallicity on its mass. So, taken together then, we can move forward with the assumption that hot Jupiters are forming via core accretion. So, where do hot Jupiters form? Here I'm showing an artist's impression of a protoplanetary disk. And naturally, there are two possible locations for their formation. They either form more or less where we see them today in situ, However, the general feeling is that it is difficult to grow planets sufficiently before the dissipation of the disk. Essentially, at these close-in separations, the gas is too hot and the heliospheres are too small to allow the growth of giant planets. So instead, the consensus picture is that these planets are actually forming in the outer icy parts of the protoplanetary disk, where ices can contribute to the quicker growth of solid planetesimals via core accretion. Although it should also be said that gravitational instability is possible at these larger separations and could actually be responsible for the directly imaged population of planets. But for today, we're going to move forward then with this assumption that hot Jupiters are forming via core accretion in the outer parts of the protoplanetary disk. We can then ask the question, if hot Jupiters form ex situ and migrate, can we determine where in the outer disk they form? And in principle, we can, because a planet's carbon to oxygen ratio will be determined by where it forms relative to different volatile snow lines within the protoplanetary disk, as indicated by these colorful circles here. This idea is perhaps most famously encapsulated in this plot by Karen Oberg et al. In 2011, which shows the C2O ratio of a disk on the y-axis against the distance from the central star on the x-axis. The C2O ratio of the gas within the disk is shown by the solid black line, and the C2O ratio in the solids is shown by the dashed black line. At the location of the water snow line, for example, you are having oxygen that is freezing out of the gas phase and into the solid phase. And this leads to a step increase in the C2O of the gas and a step decrease in the C2O of the solids. The simple idea is that a planet that accretes its atmosphere between the water and CO2 snow lines, for example, will have a different C2O ratio than an atmosphere accreted between the CO2 and the CO snow lines. However, in the intervening 15 years since this plot, it has become clear that there are a large number of complications with this simple idea that include the uncertain and evolving locations of snow lines within protoplanetary disks, the relative amount of solids to gases that are accreted during formation, and the importance of solids in setting the final C2O ratio of hot Jupiter atmospheres, the drift of solids relative to the gases in disks, and the diversity in observations of protoplanetary disks, each of which adds uncertainty along the dimensions indicated by the red arrows here. Therefore, this question remains, can composition be reliably linked to formation? And to address this, we introduced the migration method as a complementary diagnostic axis. If you look at this schematic on the left-hand side, we're seeing a gas giant planet. It's the black circle that's forming in the outer regions of a protoplanetary disk beyond various snow lines before it migrates inwards to become a hot Jupiter. There are two main migration methods which are believed for which a hot Jupiter may undergo to become eventually a hot Jupiter. The first of which is summarized in the upper right here. This occurs when the protoplanetary disk is still in place by disk migration. And ultimately, this will result in an aligned planet that preserves its primordial alignment with the disk, and thus a planet on a low obliquity orbit, where the obliquity is the angle between the plane of the planet's orbit and the stellar spin axis. The second possible migration scenario, though, actually occurs after the protoplanetary disk is dispersed and can be initiated via gravitational interactions with other bodies in the system, which can excite the planet's eccentricity and obliquity. And over time, this planet can tidally circularize, but remain on a misaligned orbit with a high obliquity. So if these migration scenarios are correct, we would expect that aligned planets should accrete more of the inner disk material than the misaligned planets, which do not migrate through the inner protoplanetary disk, thereby driving a relative compositional difference between aligned and misaligned planets. And this is precisely what we set out to test with BOWIE-ALIGN, asking the question of whether or not atmospheric composition actually traces formation. And this was a program awarded 49 hours in cycle 2. So what did we expect to see? Well, Anna Pensleen and Richard Booth did a large simulation analysis of planets forming in various disks And indeed, they ran actually 180,000 different simulations spanning a wide range of accretion and disk parameters that are tabulated on the right-hand side here. These parameters include the accretion rate of the gas onto the central star, the flux of dust relative to the gas within the disk, the Stokes to alpha number, which parameterizes how well coupled the dust is to the gas within the disk, the initial radius of forming planets, the temperature of the disk, and the fraction of solids in the disk that are in the form of planetesimals. On the left-hand side, you see the C/O ratio on the y-axis against the metallicity on the x-axis of all of the planets resulting from these different simulation setups. The data points in blue are those that finish their migration after the dispersal of the disk, and the data points in orange are those planets that finish their migration through the disk. Now, you can clearly see that there's a huge range of C/O and metallicity, depending on these different parameters, that just highlights the uncertainty in using C/O as a diagnostic of formation location. But some trends do emerge. Specifically, as you increase the amount of solid material that you accrete, which has low C/O ratio, you move to the right and downwards on this plot to higher values of metallicity and lower values of carbon to oxygen ratio. Ultimately, if you accrete enough solid material, then you would be driven into the box in the lower right-hand side, whereby you also see a divergence in the C/O ratio between the misaligned and the aligned planets, with the aligned planets having lower C/O ratios because of them accreting lower C/O solid material from the inner disk. But this wasn't the only prediction, actually, from Ahrer and Richard's paper. Ahrer also investigated what would happen if the silicates, which are oxygen-bearing refractory material, instead of evaporating upon accretion into a planet's atmosphere and releasing that oxygen into the upper atmosphere, if those silicates instead rained out of the upper planetary atmosphere and depleted that source of oxygen, then the aligned planets would actually be dominated by the accretion of the carbon-rich material from the inner disk, the carbon grains. And so this could drive the relative difference to actually be opposite, which is shown on this slide here, with the C/O of the aligned planets actually being higher than the C/O of the misaligned planets. And so again, this is something that we set out to test. So to summarize the results from the modeling paper, this here is a schematic representation of those results in C/O space, again on the y-axis against metallicity on the x-axis. Again, as I've already said, if you accrete more solid material, you'd be driven to higher metallicities and lower carbon to oxygen ratios. And depending on the behavior of silicates upon accretion, this could either drive the C/O ratio of the aligned planets to be higher or lower than the misaligned planets. But the two main takeaways from this work are, firstly, that it's very difficult to predict absolute compositions due to the uncertainties in the disk and accretion parameters and the amount and behavior of solid accretion, meaning that these sort of population level trend analyses are really what is needed to understand the link between composition and formation. And that is underlined by the fact that the models do robustly predict a difference in the relative compositions between aligned and misaligned planets. So that moves me on to actually talking about the targets we use to test this. So here are the final 7 planets that constitute the BOWIE-ALIGN sample. On the left-hand side, I'm showing the sky projected obliquities on the y-axis against the equilibrium temperatures on the x-axis of the 7 planets. The misaligned planets are shown in blue, 2 of which were observed through the GEO-3838 program, while WASP-94 was observed through Evie's separate JWST program, and WASP-17 observed through the GTO program led by Nicole Lewis. Our aligned planets in orange are NGTS-2b, TRACE-4b, and KELT-7b that were all observed through GEO-3838. And these aligned planets all have obliquities less than approximately 15 degrees. But probably the most important aspect of our survey is actually shown on the right-hand side of this slide, which are the stellar parameters, with the effective temperatures of the host stars on the y-axis against the metallicity of the host stars on the x-axis. And very importantly, all of the stars in our sample actually sit above the Kraft break. And the reason we made this choice was that planets orbiting cooler stars with deeper convective envelopes can actually tidally realign over time that erases this potential link between obliquity and migration history. So this particular experiment has to be performed with hot stars. And in this case, they are all F-type host stars. And with that, I'll pass over to Evie to discuss the observations, and I'll briefly stop sharing my screen.
Thank you. I will hope this works equally well. Can you just confirm that you can see this? Awesome. Okay. Now it's my turn, basically. Thanks. Well, James and I will split it up in a way that we can both talk about our own kind of work, but also summarizing it together. And as you can see, I'm gonna take over the observations. For those of you who know me, I love green, the color green. So this was the indication to James that we need to switch over. Was basically the slide is in green. Anyway, so the observations. I'll talk about each of the targets individually now, but before we get into this, I'm also quickly going over the individual targets again. So we have the misaligned ones always in blue, like James said, the aligned ones always in orange, and then I'll also focus on the two individual ones that have been observed for other programs. And then I want to summarize that we have at least 2 reductions and 2 retrievals per planet in the individual papers. And then in the combined analysis, we also have Tiberius and Eureka and Petitra trans, but I'll come back to this in a little bit. I just wanted to highlight that there's been a lot of data reduction work going into this with Tiberius, Eureka, and exotic Jedi as well. Okay, so let's look at the first planet. So this was WASP-15b. You will always see the planet parameters on the top and the parameters, the citations on the right, and the published spectrum is on the bottom left. This was published by James sometime last year, but there was the first observations we taken, and the transit light curves for NRS1 and NRS2 you'll see here. And then this is the transmission spectrum that we've published. We found confident detection of water and CO2 and some hints of sulfur species as well. So you see in the colors, the contributions over the individual molecules and the total model in blue. And there are some hints of SO2, which is not confidently detected, but a tentative detection. And we also found a feature around 4.9 micron, which kind of is where OCS is expected, but we couldn't confidently detect, and also the width doesn't quite match, so it's still unknown where this feature exactly comes from. The C/O ratio reported in this is around 0.53, so around solar, and metallicity is larger than solar, about 15 times. The second planet I want to highlight is P30b, which was published by Alistair Clarenbot earlier this year. They were taken in March last year. Here again, you see the transit light curve of NRS1 and NRS2, and the residuals on your right. You'll also see that the planet is the transit shape is a little bit different. This is due to the fact that it has a higher impact parameter, so we have a lot more ingress and egress time. Nevertheless, we found a really nice transmission spectrum here as well. Found some detections of some molecules, and this is the Eureka spectrum. The C/O ratio was a bit broader, but subsolar, and metallicity also subsolar. So these were kind of the misaligned examples. Now I want to talk to you about one aligned planet, which is TRES-4b, and this was published last year by Annabella Meach, who's I think in the audience as well. So this is again the transit light curve, really nice transits in NRS1 and NRS2, really nice colors as well that are used to match the orange of the aligned planets. And the transmission spectrum, similarly, nice, we find water, we find CO2, we find a carbon to oxygen ratio, again, subsolar, and the metallicity of subsolar. You might already see a little bit of a trend here in terms of C/O ratio metallicity, but don't worry, we'll come back to this later. Because now I want to talk about the problem children in this survey. So the first one is Cal7b, which actually was the second observation that was taken, and you'll soon see why I say problem child. So this planet is a little bit less inflated than the others. It also has the highest temperature out of all the planets, so it actually straddles a little bit the hot to ultra hot Jupiter regime. And here I'll show you again in NRS1 and NRS2 light curves. And you'll also see there's a little bit of a dip. And on the like kind of magenta like color and on the like y-axis on the right, you actually see the guide star data. So the guide star data of JWST, and you'll see that there was a jump there. So we find a tiny little mirror tilt event in our data that actually causes the NRS1 and NRS2 light curve to slightly jump around the same time where this mirror tilt event took place. It's also seen in the guidance data, which essentially means that all of our transit depths are a little bit more uncertain than we would have liked. This also caused that our transmission spectra were a little bit offset to each other, but I'm not going into detail right now. I'm showing you here now the transmission spectrum and the equilibrium chemistry retrieval here. The C-to-O ratio is much higher for these equilibrium chemistry retrievals, and it's also really dependent on reduction. And we find that the metallicity is slightly higher than solar. Here in this contribution plot, essentially, you'll also see that we have a really high cloud deck. So the features are actually not particularly strong above the cloud deck. So this really like challenged the retrieval analysis and really the constraints on our abundances. To make it worse, we also ran free chemistry retrievals where we had kind of the effect that the cloud deck moved much, much lower, and there was a preference for a continuum to be present like much higher up. So we like have the kind of the same scenario as in sub-Neptune I've seen a couple of times now, which is you can explain the same spectrum with a like high altitude cloud or smaller metallicity or like abundance features. To make it a little bit more like challenging, this data set has also reported some H minus absorption with Hubble. So we wanted to combine the spectrum with the Hubble observations to see if we can constrain the cloud deck with the optical wavelength ranges. But you'll see here that adding the Hubble transmission spectrum, which you see on like the left-hand side of this transmission spectrum, didn't make a huge difference. So the kind of the increase in transit depth around like 1.6 microns towards the like left in Hubble, this was attributed to H minus. And as we don't see the like essentially the end of this continuum of H minus around 1.6, we can't really anchor this, which means we also can't anchor our clouds relative to our like Hubble observations. And in the end, our carbon to oxygen ratio as well as metallicity, as you see in the bottom left of the corner plots, doesn't actually make a difference whether we include Hubble or not due to this extra like uncertainties in the H minus continuum. So like I said, problem child. Well, let's talk about NGTS2b. That is the second problem child in our like data set. The transit actually looks quite nice. No mirror tilt event here. And this has been published by Charlotte Fairman earlier this year as well, and who did an amazing job in analyzing this data as well as doing retrieval analysis. She actually found similarly, there's like it was constraints on the clouds, there was to some degree and C-to-O ratio metallicity, but there was also an issue with the individual like reductions preferring different solutions, and we had the same issue of that the feature strength were kind of too small to distinguish between metallicity and clouds. I want to show this here as well with the individual reductions. So you see in purple, this is Tiberius, and in this like turquoise color is for Jedi, exotic Jedi reduction, and you see the two different resolutions. But it kind of just shows that even though the transmission spectrum agreed really well, the retrieval actually couldn't quite like essentially like give the same result and kind of conclude on something. So problem child number 2. Okay, now to the not problem children. This is the additional data sets that we got from the other two JWST programs that were also in cycle to this one, and then the GTO data that I'll come to in a second. So this is WST94EB that has a really large inflated radius and is also a misaligned target and was taken as part of my separate JWST program. And the transmission spectrum is very precise. We get a very good C2O ratio and metallicity, and we find potential detections also for H2S and CO. And then we also combined this with WASP-17. So WASP-17 is also part of our sample, even though it was not part of, or like we included in our sample. And this is the very, I guess, famous planet, especially for the quartz clouds. But also there's been the GTO program has emission and transmission for the full wavelength range. So far published was the myriad LRS transit, the SOS transit, the eclipse of LRS and SOS as well. And the NeoSpec G395H is still underway and will be published soon. And here on the right is our own reductions that James and I did with the same kind of setups of all the other planets, because we wanted to have this like continuous and analysis that is all like consistent across the whole sample. So we analyzed all BOWIE-ALIGN samples plus the WASP-94AB and WASP-17b in the same way. Okay, so this is the family portrait now. So we've gone for all 7 planets. We have the misaligned ones on the left and the aligned ones on the right. And if you look at the transmission spectrum separately as well, this is our like kind of our sample that we're now working with. So now we have gathered all this data. The question now is, do the aligned planets and misaligned planets actually differ in composition? And I'm gonna talk you through the first method now, which is the retrieval analysis. So essentially doing a consistent retrieval across the whole sample. So back to this picture. What I've done is I've used Petitra Trans version 3 to test really different free chemistry, chemical equilibrium, NRS1 and NRS2 offsets. I've done a lot of tests for NRS1 and NRS2. I did not include it here in the slides, but if you're curious, please do let me know. I tested cloud patchiness as well and different PT profiles. For this purpose now, I'm only going to present the chemical equilibrium. As we know, our main goal really is to determine C2O as well as metallicity and its uncertainties and robustness. So this is the result. So I'm talking you through this now. So we have here our C2O ratio and metallicity measurements of all the individual planets, the same colors as you've seen before. So misaligned again blue and aligned orange. And these are the 1 sigma contours of the retrievals. And we're using here Eureka R400. Now we are looking at Tiberius R400 in the same plot. And we actually see the first thing that we find slight differences in the reduction. And as you can probably tell by staring at the colors a little bit longer, but you'll find that they are pretty much consistent across the reductions, except for our problem children, KELT7 and NGTS2b. So you see why I pointed out a lot of the difficulties with these data sets beforehand, because they are showing also in this uniform analysis, of course, the same issues in constraining the C2O ratio and the metallicity. If we now kind of collapse these and combine all the misaligned planets and aligned planets into one posterior distribution for the C2O ratio on the left and the metallicity on the right, you'll also see in the like median and the uncertainties that we cannot distinguish between the 2 samples, between the 2 populations on a significant level. So we really need greater precision to test these differences in C2O that are predicted from the formation models. So we need more data. Specifically, if I plot now the kind of uncertainty or like the difference that we need to get really the difference in the 2 populations, you'll definitely see that we need greater precision. Yeah. But one thing that we do find, and I want to point out here, and James is going to come back to this later as well, but we do find that all of this, except for KELT7, which, as we know, has issues, they are all essentially sub-solar C2O ratio. So they're basically all 0.6 or lower in their retrieved C2O ratios. There is some preference in terms of metallicity as well, to like a more like solar. So we kind of like sub-solar metallicities are not really preferred. And we are kind of like in location-wise in the like bottom right side of the plot that James showed, and we'll come back to in terms of like that it's shows the or like points towards the enrichment of oxygen-rich solids. Okay, so the question to do align and misaligned planets compositions differ? Well, with retrievals, we can't actually tell given the current precision on C to O ratio and metallicity. So what can we do about it? What are the potential causes that we can address? Well, one of them is this plot that James showed earlier, that is from Penslin and Buffetal, really shows that there are so many options in metallicity and C to O ratio. Like we have this like diversity that is astrophysical. So we maybe like our spread in C to O ratios is just also like hasn't overcome this astrophysical scatter just yet. So that could be a reason for our scatter or our like not being able to differentiate between the two populations. Another option, or the thing I've already like said many times, is for especially for Cal 7 and NGGSTB, is that we have this degeneracy between continuum, between the feature size essentially of the atmospheric scale height, the cloud to pressure with like reference radius as well. And we really need like additional data. There's just not enough information for G395H with often just one full feature, CO2, because even the water feature is not fully covered and it's just an increase towards the bluer wavelength range. So we just need wider wavelength ranges here. Another point to point out is that we do find also like that our transmission spectra aren't as precise as predicted by just using assuming photon noise. So on the left here, you see in the top the misaligned planets and the essentially the computed photon noise versus the measured noise, and it's always like higher than photon by at least 1.1 and up to like 1.4 for the worst case. Similarly, also for the aligned planets on the bottom left. If we take an average and also look into a little bit closer, where it has been suggested that excess noise also links a little bit together with group space integration, we cannot confirm that with our light curves, but yeah, 7 is not the biggest sample size. But what we basically need, we need additional observations since we're not actually hitting the photon noise, and or maybe also better methods in really getting to this photon noise and understanding our systematics better. So I want to rephrase this now in saying that not the possible potential causes, but what are the potential solutions for overcoming these larger uncertainties. And in summary, we need more targets to overcome the physical scatter. So more aligned and misaligned hot Jupiters, ideally around F stars or in this parameter space. We also need additional observations and or like wider wavelength coverage for the already observed targets. For reasons that I already said, we really need to figure out this degeneracy between metallicity clouds and the really constrain also for Celt 7, for example, the H minus absorption. So this was kind of our journey when we were looking into the BOWIE-ALIGN planets. We like had individual planets, and as we were already like writing the individual planet papers, we realized that the retrievals do not quite get to the uncertainty that we expected. So as we were doing the retrievals, we were talking about what other methods are there to really like not be biased or not be impacted by these retrievals degeneracies, and is there a way to do this more empirically? And this is now where James gets back on the spot here, and I'll stop sharing my screen. My laptop is just way too hot in this heat. It does not want to stop sharing. Oh no. No.
Thanks, Evie. Right, okay. So do you see this again? Great. Yeah, so thank you, Evie. So as we just heard then, we weren't able to separate the misaligned and aligned planets compositions in C2O metallicity space. So as Evie's just mentioned, this kind of motivated another way of looking and comparing the two populations. And so we were sort of inspired by color analyses as a sort of which have a long history in astronomy, of course, of separating different classes of object. So what I'm showing here are all of the misaligned planet spectra on the left-hand side as these sort of low opacity blue data points in the background. normalized by their atmospheric scale heights on the y-axis, which allows this direct comparison to be made. And then on top of those, in the darker, higher opacity blue data points, I'm showing the average of the misaligned planet spectra. And actually, in a separate paper that I led with James Owen, we demonstrated that it is actually appropriate to stack different exoplanets' transmission spectra, and that the stacked spectrum can be approximated by the geometric means of the individual planets' abundance ratios. Now, looking again also at this plot on the left-hand side, I'm showing 4 different photometric bins in these colorful bands here. We have the L band, which is mostly probing water for these planets in blue, a band centered on SO2 in purple, CO2 in orange, and then CO in red. And then on the right-hand side, I'm showing one particular color diagram with the CO minus L color on the y-axis against the CO2 minus L color on the x-axis. And you can see that the misaligned planets are quite spread out in this color space, mostly owing to their variation in their CO2 absorption strength relative to their water absorption. But of course, we're interested in how this compares to the aligned planet spectra. So I can add now the aligned planets to this color space. Again, on the left-hand side, I'm showing each individual aligned planet spectrum as the low opacity data points, with the average of these shown in the high opacity data points. It's interesting to note when you look at the right-hand side color diagram that the aligned planets appear to be clustering in this particular part of the color space. And actually, if we do a direct comparison of the aligned and misaligned mean spectra, we can kind of investigate this a bit more. So looking at the left-hand side, the comparison of the 2 means, we see that at first glance, they appear to be quite similar. But actually, there are some interesting color differences. And specifically, the misaligned planets show an enhancement in their CO2 minus L band color at the 3.7 sigma level. Essentially, they have stronger carbon dioxide absorption features and weaker water absorption features relative to the aligned planets. They also show enhanced SO2 minus L band absorption at 2.6 sigma level and enhanced CO2 minus CO absorption at the 2.4 sigma level. And furthermore, we've investigated, and each of these color differences is actually robust to pipeline choices, offsets between NRS1 and NRS2, and leave one out analysis in the construction of the average spectra. If we look at the y-axis on this color space, though, the misaligned planets show only a weak enhancement in CO minus L color at the 1.1 sigma level. And in fact, this is actually sensitive to pipeline choices, offsets, and a leave one out analysis. So what do these colors mean for potential compositional differences? Well, we can add colors based on chemical equilibrium forward models to this color space in these black lines now on the right-hand side, with varying metallicity and C/O ratio. Essentially, as you increase in metallicity, you move to the right on this color space as you add relatively more CO2 absorption feature strength relative to water. And as you increase in C/O, you move diagonally to the upper right. Taken together then, these colors are suggestive of the misaligned planets as a population having higher metallicity and with a greater spread in their metallicities with respect to the aligned planets, and potentially higher C/O ratios, although of course that needs much more data to really test. But looking at the entire population, something that is similar to what Evie showed in her retrieval analysis is that as a population, all of the planets appear to be mostly consistent with high metallicity atmospheres and low carbon to oxygen ratios, which again is suggestive that enrichment by oxygen-rich solids is important regardless of these planets' migration histories. And furthermore, we did another test and we find that these color differences are unlikely driven by other differences in the properties of the planets and stars, nor by differences in relative limb asymmetries or in cloud coverage between the aligned and misaligned planets. So if we compare back to then these the schematic representation of our formation models, then The Bowie-aligned planets appear to be inconsistent with this unmixed gas-dominated accretion scenario because the high metallicities and low carbon to oxygen ratios that we're inferring is pointing towards solid accretion being important. From the colors, the higher metallicities that could be implied for the misaligned planets could reflect their formation in the larger solid reservoir of the outer disk, with the greater spread perhaps resulting from more diverse formation locations for the misaligned planets. Again, highlighting that these two results are purely seen in the colors. But ultimately, more data is needed to test any relative C2O difference between the aligned and misaligned planets. Now, moving on to a slight aside then, could we use the colors as a diagnostic for the migration history of other planets? So here again are the Bowie-aligned planets in color space. And here are the colors of other hot Jupiters with JWST near-infrared spectra. Looking at HD 189733b and WASP-39b, we see that these planets both have aligned orbits, but their colors more closely match the misaligned planets in the Bowie-aligned sample. And so we can speculate that these planets actually underwent high eccentricity migration, followed by tidal realignment around their later spectral type host stars. While HD 209458b, on the other hand, has both an aligned orbit and a color that places it within the cluster of aligned Bowie-aligned planets, which means it could have just migrated through the disk and preserved a primordial alignment. Taken together, then, we can speculate that the Bowie-aligned colors could inform the migration histories of hot Jupiters more broadly. So, returning to this question then of do aligned and misaligned planets compositions, well, from our color analysis, the answer does appear to be yes. Although, of course, this is in contrast to the retrieval analysis. So, in summary, the formation of hot Jupiters remains uncertain, and we've performed the Bowie-aligned survey comparing aligned and misaligned hot Jupiters to use migration method as a complementary axis. However, our retrievals cannot yet separate the populations in C2O metallicity space and ultimately need more data to test the predicted difference in C2O from our formation models. However, the colors imply that the misaligned planets are more metal rich with greater spread in their metallicities, which could be suggestive of them forming in more diverse locations within the larger solid reservoir of the outer disk. On the whole, though, both colors and retrievals are suggesting that the population appears to be consistent with solid enrichment regardless of alignment. And I finish by mentioning that the Bowie-aligned colors could inform the migration histories of other hot Jupiters. But ultimately, we think that Bowie-aligned has demonstrated that combining atmospheres with alignments offers a promising new window into learning about the link between formation and atmospheric composition. And with that, we'll gladly take any questions. Thank you.
Thanks, both James and Evie. That was really great. So, well, that was quick. William, we have a question. You can feel free to unmute yourself.
Yeah, great. Thank you very much both for the talk. I was curious if you had given any thought to what that one misaligned planet that was very far left on the color diagram was. Whether is that an exception, or do you think something strange is going on there?
Yeah, Evie, I guess I'll take that one. So yes, you're referring to HAT P30, which is this one down here. And
Right.
in fact, HAT P30, as Evie mentioned, also comes out as having a particularly low metallicity and low C2O ratio. So both the retrievals and the colors seem to be kind of pointing in the same direction for this one. In this case, we don't really know exactly why it sits down here. It could be indicating just this inherent diversity within the misaligned planet population, or we could go one step further in our speculation and speculate that actually maybe this planet is one that migrated through the disk, but that the disk itself was misaligned.
Mm.
But we can't really be sure about either of one of those scenarios.
Yeah, thank you.
Other questions? Avi.
Yeah, great talk, guys. Both parts of it. Really interesting to see the different analysis strategies. Considering, and this my question is not at all to be negative about one side or the other here, but obviously retrievals include a lot more complexity and correlation analysis between sort of complex model parameters compared to a color analysis, and the fact that you're not seeing correlations in a many more higher dimensional analysis compared to color, wouldn't that suggest that maybe there's more going on compared to just these few dimensions of Z and C to O that you might be seeing a correlation in? I'm only saying, are we overinterpreting? Is there the chance that we're overinterpreting these color results essentially?
That's a very good question. I guess I can respond immediately, and then Evie can add any additional points she may wish to. So, as Evie mentioned, of course, we had a lot of difficulties with some individual planets on the retrieval side that really, challenged our ability to measure precise C2O ratios and metallicities for some planets. And in fact, in the case of WST-15b, for example, sometimes the metallicities from the retrievals were getting driven to such high values as to be no longer consistent with hydrogen-helium dominated atmospheres. And so in those cases, we actually had to, in fact, for all of the planets, we ended up running interior structure models from Daniel Thorngren, which allowed us to place upper limits on the atmospheric metallicities. And in some cases, the retrieved metallicities would pile up against those priors. And I think that really points to retrievals struggling in many cases with this particular wavelength range. So that motivated this more model independent way of comparing the spectra. In some cases, perhaps the retrievals are just overly complex given the limited wavelength range we have. Considering the color comparison, I think that it's fair to question whether or not the colors are probing the exact compositional differences that we've posed here. But I think that the colors are revealing some compositional difference, although tying it down to specific metallicities and C2Os with these simple chemical equilibrium forward models is a simplification. I think we appreciate that. But that said, that we did test other differences in color space, whether or not these colors could be driven by differences in the masses, differences in cloud coverage. We tested, for example, whether or not all of the aligned planets are cloudy and all of the misaligned planets are not cloudy. And all of the aligned planets have limit symmetries and all of the misaligned planets don't have limit symmetries. And you basically can't construct a color diagram that leads to separations without there being some compositional difference. So I think that in summary, I think that there is some difference there. It's just that we can't say exactly what it is, and it obviously isn't coming out in the retrievals just yet. I don't know if Evie wants to add anything to that.
Yeah, I wish if you have any ideas of combining something that is retrieval but also color, something a bit more I don't know, empirical driven, it's happy to take suggestions.
No, I really like that you, as you say, you have these very much more agnostic strategy and just looking for trends. That's obviously a very foundational way to do things, and then comparing it to what more model dependent work or sort of analyses. So I think it's great. As James was saying, just trying to continue to bring them into alignment, so that you expect that what the results from one say connect with what you would expect from the other one. Is I think it points to more both model development and, as you guys repeated, the more and better data. So Yeah, great overall work.
Thank you. I liked how you said
Yeah,
bringing them
thank you.
into alignment.
Yes, pun intended.
Yes.
Okay, other questions? I will ask a follow-up question. So obviously everything you've discussed here is solar. You, I presumably, there is some variability in the stars themselves in terms of the elemental compositions. Do you know to what extent that they actually vary within your sample?
Evie, would you like to answer, or should I?
I mean, James, you have the backup slide. I know you do.
I do, yeah. Let's see, it's in here somewhere. Not that one.
We have many backup slides.
Here we go. Yeah, I know. I've just been making so many slides over these last few years and just keep on appending them. Okay, so this here is a comparison of the stellar parameters essentially in two different color spaces. So the rows show the color and the columns show either metallicity or C to O ratio of the stars. And for 3 of the stars, they have measured C to O ratios. And for the remaining stars, we used empirical relations between metallicity and C to O calibrated for other stars. But essentially, there is not really, there's no significant difference in the metallicities between the aligned and misaligned host stars, with a slightly higher C to O ratio for the aligned stars than the misaligned stars. And so we kind of take this as evident, or our conclusion from this is that the planets are not simply inheriting the compositional differences from the stars, which would instead potentially favor the aligned planets having higher metallicities and the aligned planets having higher C to O ratios, which is not something that we see in the planetary compositions.
Yeah, maybe to add here as well, we have a similar plot for the retrievals as well, where we plot planetary retrieved C2O ratio versus stellar C2O ratio from this work as well, like the same stellar C2O ratios. And we couldn't find any correlation in there.